Good afternoon, everyone. It's 16th of December 2025, Tuesday, 3:30 p.m. here. In this video, I'll be talking about some interesting facts about the nodal point, not exactly nodal point, but visual angle and its clinical significance. See, in books, it is given like it's the angle made by the height of an object, that is vertical orientation. It should be vertically oriented and it should be like its height, it should be perpendicular to the it's not optical axis, actually it's a visual axis. It's not given in any book. I have to search in different articles on internet, so it's not given in any book that this is perpendicular to the visual axis. It is perpendicular to the line of sight, and line of sight, it is the line that passes through the fixation point through the center of pupil, and it doesn't extend to the fovea. But visual axis, it is the line that passes from the fixation point through the nodal point to the fovea. And optical axis, it is the line that passes through the center of curvature of if it is a spherical lens, it is the center of it passes through the center of curvature of a lens. And if it is a thick lens, center of curvature of two or three more lenses. So it's the line that passes, and all the principal points or cardinal points like focal points and principal points and nodal points for thick lens system, they all lie on the optical axis. But the focal point of the human eye, it is not on the optical axis, it is shifted temporally and inferiorly. So we get the first Purkinje image that is equivalent to this fovea, that is nasal and superior to the optical axis. And that angle is called as angle alpha between the visual axis. Visual axis is the line passing through the fixation point, nodal point, and extending to the fovea. These are the things you should know. What is angle kappa? Angle kappa, it is the angle between the pupillary axis and visual axis, and it is around 3 to 5 degree, and it's important in myopes and hyperopes. Usually it's 3 to 5 degree. In myopes it is negative, that is usually it is nasal, but its temporal shift is seen in myopes, and in hyperopes it is more nasally shifted and it is more positive in, that is more nasal in hyperopes, and in myopes it is shifted temporarily. So it can be positive, it can be negative, depending upon its like how much shift is there. So that was about the angle kappa and angle alpha. Why it's important? Because this visual angle and the object that is vertically oriented, it is vertically oriented with what axis? Optical axis, visual axis, line of sight, pupillary axis. It is said in one of the articles I saw in on internet. It is not given in any book. It's vertically oriented with respect to the line of sight, or clinically line of sight and visual axis are taken equivalent. Okay, and even angle kappa and angle alpha are taken equivalent, almost equal. So point of intersection of the line of sight with the cornea, it is where we see the first Purkinje image, that is her corneal reflex. So this is the line of intersection of the line of sight with the cornea and not the visual axis. But the visual axis and line of sight, the angle is so small then, and that's why it's almost taken as the visual axis intersects the cornea at the first Purkinje image. So it's very important to know. Why it's important to know? Because this object orientation, vertical object orientation, or Snellen's chart optotypes, or any visual acuity chart optotypes, they should be vertically oriented uh, to ensure the fixed distance from the nodal point of eye, and the chart should be vertically oriented and not tilted. Its plane should be perpendicular to the line of sight or visual axis. We are not taking into consideration the optical axis, because the fovea, the rays, where they should be focused at fovea, where the brain can perceive the image clear as a clear image, where the maximum resolution is present, and it doesn't lie on the optical axis, this fovea. It lies temporal and inferior and projected as first Purkinje image, the corneal reflex, that is nasal and superior to the optical axis. It can be seen like that. So that was about vertical orientation with respect to the line of sight. A line of sight, you take it as visual axis because the angulation clinically is almost negligible. The plane of the visual acuity chart should be perpendicular to ensure the fixed distance from the nodal point of the eye. So when it is at fixed distance, because when it is tilted, the upper like this, when the visual acuity chart is tilted like this, suppose, then upper optotypes, their distance from the nodal point of the eye is going to change, and the lower distance is going to be, closer. It will be tilted forward and upwards. We are not taking into consideration the upward shift. We are taking into consideration the forward shift, linear distance, like this, horizontal linear distance we are taking into account, because to decide the visual angle we want the linear distance from the object and plus vertical dimensions. So vertical dimension, height of an object. So if the height is if it is 5 centimeter, suppose this is an object and it is 5 centimeter object, and it is tilted like this, it is like this, it will have tan theta value, and it is tilted like this. Now this lower end is shifted forward, upper end is shifted backward. So how it's going to make difference, how it's going to make difference with the visual angle that it makes at the nodal point of the eye, that I'm going to show in diagrams. It's very interesting and it's not given in any book. It is just for the curiosity purpose and better and deeper understanding, and to have the clear concepts. I had to draw nice diagrams. I had to confirm it with some articles on the internet, Google information and internet, because it's not given in any book. So I couldn't refer any standard book for these interesting facts. So let me show you some handwritten diagrams by me. See, for thin lens, we know that this is the optical axis that passes to the center of curvature, from which the lens is taken when it's a spherical lens, and B is the optical center. And if it is a perfect sphere and perfectly symmetrical thin lens, then optical center, principal points, they all coincide. Nodal point is, this concept is not for the thin lens. Now optical center, the rays passing through the optical center, they remain undeviated with respect to the optical axis. See, this theta 1 that it makes this incident ray, it should be like this. This incident ray at the optical center here, okay, making theta 1 angle, and this theta 2, these are same. Theta 1 equals to theta 2 because there is no angular deviation, there is no linear displacement, and that point is called as optical center. It coincides with the geometrical center and principal center. Principal point, it coincides with the principal point and geometrical center of a lens if it is thin lens and perfectly symmetrical lens from an ideal sphere, which is spherical lens. Now that was about the optical center, optical axis. And this optical axis, it passes to the optical center, and then principal point and center of curvature of a sphere if it is a spherical lens. Now that was about the thin lens. Now about thick lens. In thick lens, this optical center gets broken into 2 points, which are called as nodal points. These are the principal points. Principal points, it is the point of intersection of the principal plane with the optical axis, where they are perpendicular to each other at this point, and principal plane where the rays appear to be refracted, that plane of refraction. I have already made a video on cardinal points of eye and cardinal points of a lens system. You can see that. Now these nodal points N1 and N2, you can see this optical center concept gets broken into 2 nodal points, and at nodal point, if this is incident ray, it makes an angle theta at the nodal point of eye with optical axis. And then this is N2, this ray travels like this towards N2, and then it is refracted like this. Then again refraction happens here, refraction happens here, here, everywhere. But when it is incident at the nodal point 1, it will make an angle theta 1 with respect to optical axis. Then the ray will travel straight towards the nodal point 2nd, and then it will make angle theta 2. It will undergo refraction within the substance of a lens, then theta 2, and theta 1 and theta 2 are equal because there is no angular deviation or angular displacement occurring when the ray hits nodal points in thick lens system. And theta 1 is equal to theta 2, but you will see rather than going like this, it's going like this. There is a lateral shift, but there is no angular deviation. So linear deviation is present, but angular deviation is not present. Linear displacement is present, angular deviation is not present. Now this is an object, okay, it is placed vertically, like how the letters are in the visual acuity chart. Visual acuity testing charts are placed. It's plane, the visual acuity chart, its plane is perpendicular. Here I have shown the optical axis, but it is actually, for human eye, it is the visual axis and not exactly optical axis, okay? You remember that thing, because we want the focal point, okay, and that lies, nodal point and focal points, they lie on the visual axis. So visual axis and line of sight, because line of sight, point of intersection of the line of sight with respect to the cornea, point of intersection of the line of sight at cornea is actually called as corneal vertex, and it is it is the site where we see the first Purkinje reflex or corneal reflex. And the angle between the line of sight and visual axis, it is so visual axis lies nasal to the line of sight, and the angle is so small that you can say the visual axis, it intersects the cornea at the corneal vertex only. It doesn't, but clinically we can take it as the same. So I have referred this from 2 of the standard books, which I'm not going to mention here now because my work is stolen, so I'm not going to mention that thing. And then now suppose this optotype or any object, it is vertically oriented with respect to visual axis here, that is passing through the nodal point, and here I have shown optical axis, but you say it's like it's going to the fovea, no nodal point of the eye. So whatever may be the case here, you see that this vertically oriented object with respect to the visual axis. Now visual axis, if it is visual axis, then here will be the fovea and not temporally. I have shown the optical axis, but you just take it as visual axis. Now this is perpendicular to the visual axis, and suppose this is the fovea here, this is the fovea here. Now this should be perpendicular, then only we can use the tan, cosine and sine functions, because to use these functions we need a right angle triangle. So Now this is like this is the visual axis, suppose, and this is one triangle, this is another triangle. Now this angle is this big. Okay, now we cannot directly imply this tan function on this. First we will have to imply tan function for this triangle, that is theta 1, then for this triangle, then that is theta 2. Okay, now you see this ray passing through this, and this is the reduced schematic eye where the two nodal points average is taken, and it is reduced to one nodal point for simplification process. And this nodal point, the distance of it from the fovea is taken as 17 mm, and from the corneal pole, that is point of intersection of optical axis with the cornea, it is 5 mm, 5.5 mm. Now this theta 1, that is this ray making with optical axis or visual axis, you say, optical axis you say, this is theta 1. Okay, now this theta 1, or you say visual axis, this is theta 1. Now this theta 1 is equal to this angle here. Okay, now this r1 angle is equal to this r1 dash angle, and this r2 equals to this r2 dash. Now r1 is equal to r1 dash, r2 is equal to r2 dash. So these two angles and these two angles, these are same, because there is no deviation that takes place at the nodal point of eye. There is no angular deviation of the rays that takes place at the nodal point of the eye. So these two angles, be it visual angle taken from the object side or retinal side, this is going to be the same. So this is very interesting fact that I discovered, which is not mentioned in any book that I have read. I had to take reference of, I had to take reference of some articles on Google, and there are some equations which are given in the book. From that I concluded that these two angles are same. Now we'll see. Now this theta 1 is made up of r1 and r2. We cannot directly imply this tan function, and how we can directly imply this on this, we'll see here. Now theta 1 equals to theta 2. Okay, now theta 1 is what? r1 plus r2, and theta 2 is equal to r1 dash plus r2 dash. Now tan r1, we can use this tan, cosine, sine functions only for right angle triangles. So this is a right angle triangle, and that's why it needs to be vertically oriented and perpendicular with respect to the optical axis or visual axis. In human eye, you take it as visual axis. Now tan r1 is equal to height opposite upon adjacent. Adjacent is what? Hypotenuse is the largest side, we just ignored this. Tan r1 is h1 upon d. h1 is this, h2 is this portion of an object, and this is entire height, and it falls in the depth of the focus, entire object. Now tan r1 is equal to h1 upon d, tan r2 is equal to h2 upon d. Now tan r1 plus r2 is tan theta, h1 plus h2 upon d. This comes like this, this equation comes like this. Now this h1 plus h2 is nothing but the height of an object. So tan theta becomes height of an object upon distance of an object from the nodal point of the eye, and tan theta 1 is equal to h upon d. And similarly you can derive the equation for this. We'll have to use the arc, but if it is a small arc, we can directly we can similarly imply this equation here. It's like a curve of a circle, and you can take it as a straight line because it is very small. You take it as a very small thing, and then as a side you can, linear side you can say, and if you apply the same equation, it comes to be as tan theta 2 equals to h1 h dash divided by d dash. This height h dash, entire height, upon d dash, because it's perpendicular. Okay, Now theta 1 equals to theta 2, so h upon d equals to h1 upon d1. That is, this upon this equals to this upon this, because these two are equal. So from this equation in the book, you know that this angle on the visual angle on the object side and visual angle and this angle on the retinal side, it's going to be the same. So this is same, and this visual angle depends upon height of object. It is directly proportional to the height of object. If the angle is more, then the object seems bigger. If the same object is at distance, and visual angle is inversely proportional to the distance of an object from the nodal point of the eye. If it is more, then visual angle will be less, and the object will look smaller in size. For example, the same object size, for example car, a number plate of a car, it is going away from our eye. Though its dimensions in the real world are same, it seems, smaller and smaller progressively as it passes away, and from that we can predict its speed, how fast it's approaching us. Now this is very interesting. It's nowhere given. I had to derive this because it was my curiosity. How to get this visual angle if this object is not vertically oriented in the visual field with respect to the visual axis. So I had to draw the diagram, and I had to literally take some values and draw some conclusion, and its clinical significance also I got. So I'm very much curious to share this thing which I have discovered and which I have mathematically represented here with all of you, so that you can understand it, why it needs to be vertically oriented object, and what is its clinical significance as long as visual acuity testing is concerned. So suppose this is an object or optotype of 5 cm in length, and it is the visual axis, it is the nodal point, it is the fovea of human eye, this is nodal point, and it is the fixation. So it is the visual axis, and this object is oriented vertically with respect to our visual axis or line of sight, because line of sight and visual axis angle is so negligible that clinically can be taken as same. So it is, now if it is passing to this visual axis, this perpendicular, we can use this tan inverse function to calculate this theta angle in degrees. You can calculate in radians also, it's always there. And it's very interesting that suppose this tan theta function is very important if it is right angle, and it's always for the right angle triangle. Suppose we want to know this angle, okay, this is hypotenuse, this is adjacent, and this is hypotenuse, adjacent, and this is opposite. Okay, now we want this theta. Tan theta is opposite upon adjacent. Okay, this is opposite upon adjacent, and this is the largest side. Now this tan theta value opposite, suppose it is 1/2, it is 1 centimeter, and this is 2 centimeter. Okay, 1/2 is 0.5. okay, so its tan theta will have some around 26 point something degree value. Okay, so theta, it is 0.5, and if we want to know theta in degrees, we'll have to go for tan inverse of 0.5. Tan inverse of 0.5 will be around 26 point something degree. You see, it's around 25 to 27 degree angle. So for this 1/2 ratio, this angle is always going to be constant. For example, if this theta is there, and if it is 1 centimeter, if it is 2 centimeters, it will be opposite upon adjacent, it will be 1/2. And if it is suppose what 4 cent if it is 4 centimeter and if it is 8 centimeters, okay, it is right angle, and this is 4 and this is 8 centimeter, opposite upon adjacent. Now this angle here and here, it's going to be the same, because tan inverse of 1 by 2.5, it's always going to be some 26 or 27 degree. You see, it's always going to be this value. So that function is called as tan function. Okay, so for 0.65 also there will be some ratio, or 1 by 1 also is going to be ratio. Okay, this 1 by 1 tan 1 equals to what, you'll have to see that thing. So it's this ratio 0.6, for example 0.5, it's almost 29, so 0.5 must be around 27, 28. So whatever is the ratio, whatever is the length, it's always going to be the fixed one, and this angle is going to be fixed one for this kind of ratio, for a particular ratio. And from this they have derived this formula tan theta, and it has clinical utility. I have shared one of the YouTube video links which I liked to see the practical use of tan theta function in real life. Okay, so this is vertically oriented, and we have derived this equation tan inverse h upon d. And how we have derived this h upon d, we have already known here before. So tan inverse 5 by 8, tan inverse 0.625, it comes to be 32. So this vertically oriented 5 centimeter object at distance d makes an angle of 32.0053832 degree. Now suppose this same 5 centimeter object, it is tilted, it's not vertically oriented with respect to visual axis. Then what will happen? Then obviously this end is, now this end has gone farther away from this end point, nodal point, and this end has come closer. It has come closer, and it is also vertically elevated. We are not concerned about vertical shift, we are concerned about this horizontal shift. Horizontal shift, it has come closer to the nodal point, it has gone farther. But for this kind of triangle, which is not a right angle triangle, now we cannot use this tan theta function here directly. So we'll have to draw a perpendicular. We have to convert this triangle into two right angle triangles to use the same formula. Like this tan theta 1 will be h1 upon d dash now, and this tan theta 2 dash will be this h2 upon d dash, and then this tan theta becomes h1 plus h2 by d2 d dash, sorry. Now this h1 plus h2 becomes h divided by d dash. So tan theta, this new distance, here it was 8 centimeter, and now this new distance I have measured, it is some 8 point something something. I have taken it as 9 centimeter, okay, for convenience, for mathematical simplification. So obviously the average resultant is towards this end, so the distance is increased. So distance is increased means what will happen to the visual angle, we'll see. Now this tan theta, first for this we'll calculate, we have calculated 32.0053832 degree, 32 degree. Now this new tan theta 1 here, okay, I want to see whether it's going to make a change. Obviously distance is changed, so this angle should be changed. So tan theta 1 equals to h upon this perpendicular drawn to this height of an object that is tilted. As tilted, that is towards the upper end, means distance is increased. If it was like this, if it was tilted like this, downward shift and tilted, then resultant would be on this side and distance would decrease. I could have shown another diagram, but I hope you understand this. Now tan theta dash equals to h, this h upon d dash. This h is 5 centimeter, this d dash is 9 centimeter, new distance. This ratio is 0.555. Now theta in degrees, tan inverse of 0.555 comes to be 29.03. Now see, the distance is increased and theta is 29, and here the distance was 8 centimeter and theta is 32. So with tilt, backward tilt like this, the resultant comes to be near the end that has gone farther. So obviously this normal is distance is increased, so as visual angle is inversely proportional to the distance, so visual angle, the distance is increased, so visual angle is decreased. It was 32 and this is 29, and that's why, suppose this is visual acuity chart, this is visual acuity chart, okay. Now what's the clinical significance of it? Now this is the visual acuity chart, ETDRS chart, okay. So if it is tilted like this, now the upward letters will be at more distance. The distance of upward optotypes means the symbols, letters or numbers of standard size proportion which are used to test the visual acuity on visual acuity chart. So letters which are standardized proportion to test the visual acuity are known as optotypes. So these are the optotypes, letter optotypes, which are used on ETDRS chart. Now this should be, its plane should be perpendicular to our line of sight or visual axis, so that each optotype will have similar distance to the nodal point of eye. So we can compare the visual angles, because if at a fixed distance, because if it is tilted like this, the letters are tilted and the upward letters or optotypes are at more distance than those optotypes or letters at down there near the bottom end, okay. So it's going to alter the distance, and when the distance is altered, we cannot compare the lines and the visual acuity will be affected. The visual acuity takes the visual acuity at fixed distance for each optotype. It's very, very important to keep the constant distance. So that's why this plane should be perpendicular to the visual axis or line of sight. So that's the significance of it, and that's why I have shown this diagram, and this kind of explanation is nowhere given in the book. I hope you understood this, and it's going to help. And how you derive this equation also, like directly they have given this portion only, like this portion only, but object is never up to this angle only. It goes even downward to the visual axis like this. So you'll have to use two tan functions, and it comes to be the same, like theta equals to this height upon this distance. And how it comes, I have already shown this here. I hope you understood this. Its only significance with respect to vertical orientation of the visual acuity charts with respect to the line of sight or visual axis. Visual axis is the axis that passes through the nodal point of eye, fovea and the fixation point. I hope you got it, and I'm very glad to explain these all things to you, even the tan inverse function. Bye. Take care.